It's that time again. So we continue this afternoon with Igor Pak, who's talking about the combinatorics and complexity of Stanley's inequality.
Thank you, Alan. Thank you, everybody. Major thanks to the organizers for inviting me. I think I'm standing in the line. So thank you those for joining here. Thank you those for joining by Zoom. And of course, thank you, Richard. Mentorship cannot be described in half an hour, so I'm not going to do that. I'll tell you some maths and I'll tell you some stories. They recite just one story. Everyone prepared for the story? Okay.
Ready.
So I've always been interested in things about related to combinatorics and complexity. And one thing I found curious is whether Richard had anything to do with computational complexity. I couldn't believe that in the last 50 years, since the field exploded, he hasn't made a major impact. So I became curious, and one night, as people do, I'm sure, I was sitting at home, drinking beer, and watching one of the Don Knuth's videos online, which I recommend. And this particular video was in some Richard Clark's Berkeley conference. And he mentioned that in the very first talk which Clark gave about anti-completeness, Richard Stanley was in the audience. So I didn't believe him, because I naturally don't believe stuff. So I wrote to Richard, is that true? And he replied, basically, he didn't know. And apparently he was not impressed. So I let it go. A couple of years later, Richard wrote to me back and said, "Oh yeah, I visited Don Knuth's house, and Don Knuth had a record of everyone attending this webinar. And with this arrow, you can see Richard did attend the talk, so there's a proof he wasn't impressed." Yeah, this is sort of a follow-up. Richard's email also talked about how he could have, in principle, started doing anti-completeness because he was accepted at Stanford to do that kind of stuff. However, because of various personal issues, he had to decline the offer. I hope Don forgave him at some point. I'm glad to see it worked out okay part. That impressed me the most. I was slides on
very, very low probability.
So anyway, that is the end of the story. I hope everyone can now join into some math, and I'll talk about one inequality and one result by Richard, and that is I'm going to talk about linear extension. Linear extension is a bijection from the ground set into numbers from 1 to n, the size of the set, which are order preserving. So f of x is less than f of y if x is less than y, and E of p, the number of linear extensions. You've seen this before, so I'm assuming that you're going to be okay if I just move on. And so here is an example. So here is a tiny little pocket of 4 elements, and that happens to have 5 linear extensions that sort of grow kind of down, except for this one that so the order goes down, but 3 is actually not incomparable with 2, so it can be bigger. Everyone okay with this? Okay. Well, raise your hand if you're not. So we need another definition. I'm going to fix one element x, and I'm going to look at number of linear extensions which take a certain value a on that element x. That is the only definition you need to remember. And And now here is an inequality. This is the same inequality that Pete Winkler was talking about as being impressed. The inequality starts the sequence of concave. Okay, everyone clear about the statement? So that's completely innocent. Doesn't look fancy, doesn't look like a big deal at all. It did solve a conjecture. It solved the conjecture. So unimodality was conjectured by Kislytson, and the concavity was later conjectured by Chang-Fried and Graham. And it's sort of the importance of the solution cannot be sort of measured by the fact that it was obtained soon after it was taken. Okay? It's just an amazing, amazing result. And that's all I'm going to talk about. Everyone good with this? I want to see it happen. Okay, excellent. Thank you. All right. So this is an example of basically you understand. So you get 2 to 1 and 2 to 1 sequences of concave. Let's move on. So, so in reality, Stanley proved a much stronger inequality. So suppose not only you look at the element X, but you also fix elements C1 up to Ck and numbers C1 up to Ck. So, so N of A looks at the value of linear extension on X with a lot of other values being fixed. And you get the same log concavity result. I'm even writing it in the same way, and this is the paper, as you can see. Okay, so good. So now here is the whole proof. This is the sketch of the proof from a later paper by Richard, and basically the theorem 4 is Alexander's chemical inequality. The proof is basically very short. And it's not even the only result in the paper. The paper has other applications, but that result is miraculous because you see it's an application of convex geometry to numerative combinatorics, and that is something that people have trouble understanding ever since. So it's been over 40 years. And that's proof. And I personally spent, I don't know how many previous years, maybe 4, trying to understand this inequality. And I'm not going to tell you everything, I'm just going to tell you one thing that the proof is. Okay, so everything is going to be about this inequality. All right. So now, before I do that, I want to tell you some related inequalities, and so naturally, as an analog of the number of linear extensions, one can consider the order polynomial. Order polynomial is another order preferring maps to numbers from 1 up to t, and so it turns out that it's a polynomial of t. And it turns out that there is a similar, sort of similar inequality that Francesco Brandi proved in his dissertation. It turns out that the order polynomial is not okay, which is sort of remarkable. But even more interesting, this one has an injective proof. That's how Francesco proved it. Just direct injection. Okay. So raises the question, what's going on? Can you prove other results like that? And the answer is yes. So they can Patterson prove the similar result. Instead of so now they consider order polynomial and they look at the value of linear extensions on some element, and turns out that there's a concavity in sort of similar ways that Stanley inequality works. Okay, everyone okay with this? And again, you should be looking at this line over there. That can be proved by direct injection. So they didn't stop here. They continued. You can sort of follow this pattern and fix a whole bunch of values, a bunch of other elements. That still can be proved using direct injection. I'm not going to tell you obviously how to do it. It turns out that this particular log concave inequality can be proved by injection. So, which raises the question: how can Stanley's inequality can be proved by injection? That's an actual question to ask, right? And that's the kind of thing that we do. So let me give you kind of mathematical explanation how we do things by injection. So suppose you have injection from left to right, then the size of the left is less or equal than the size of the right. Hope all of you are with me on this. And people looked into that. Usually, people don't talk about their failures. This is sort of one of the downsides of reading old literature. But the DDP actually did write about their failures. They wrote it's unlikely that standard inequality can be proved using direct injection. At least the way the kind of injection presented in that way. And remember, they checked it. They proved a giant inequality using direct injection. Okay, not an easy one. Used, in fact, in that paper, they rediscovered promotion and demotion, which they called it something else. But if you look at it, they proved a lot of properties of promotion and demotion. It's a good paper. So anyway, so the point of the talk is I'm going to answer that question. Okay? You think it's going to be yes or no? Yes?
Unlikely.
No?
Yes.
I see different opinions, so I'm glad you don't know. So I'm gonna state the same theorem about 7 or 8 times, and this is and we're gonna try to. This is going to be our slow way of understanding why not. Okay, so the answer is no. And that is the statement. There is no injective proof of standard inequality. I put the word nice there because otherwise you can always order electrographically things from left to right and make it an injection. So one should ask, what is nice? You want to know? So let's make up a definition. This is sort of what people do when they need to define stuff. And so we're going to say that injection is nice, suppose injection and the inverse are polynomial time computable. And so in particular, we should be able to figure out if something does not have a preimage. Okay? So we want that to be polynomial time computable, and for cryptographic purposes, this is kind of typical. All right. Now, now we can now that we put it in a computer science framework, we have more trouble. Obviously, you should never. Every time you see somebody talking about some statement in computer science, you shouldn't take it as a face value. It's based on something. So basically, we're saying there's no nice injective proof unless some issues in computers. Okay. So this is my level 1 of understanding of our theorems. Okay, there's going to be many more. So get prepared. We're not done. Nowhere close to be done. I'll bring you to the shore. Yes. You'll see. Be patient. You'll see. So let's remember that a nice injection gives a combinatorial interpretation for the difference. Indeed, in this particular case, number 3 is a combinatorial interpretation for the difference between the sizes of two sets. You see? You hope you all agree with me. This is literally the size of the number of elements which don't have a preimage. Now, if it has, now we're gonna hold off on something bad, and we're gonna replace this that does not have a combinatorial interpretation. Okay. So I'm saying that the difference between left-hand side and right-hand side does not have a combinatorial interpretation. If we could prove it injectively, it would have a combinatorial interpretation. So now it doesn't. You with me?
Yes.
Okay. I feel you're stunned. This is like a new idea. I'll give you 2 seconds to figure it out. Done.
What is NFA?
What?
What is NFA?
NFA was the main thing. That was the number of linear extension which takes certain value at an element. So remember, that was one inequality that we're talking about. The inequality was the inequality, standard inequality stated that this square minus this product is greater than 0. That's what and we're saying that if you had a nice injection, so for example, for matching numbers, you can go look up Christian Kratman-Haller's paper. He has a very nice injection which inject one side, smaller side into a larger side, which does give a combinatorial interpretation of this. and we're saying that it's not possible for those numbers. Okay? And now, one thing you should ask, what is the combinatorial interpretation now? And that one I have an answer. It's a very long answer with a very few letters. Okay? So I wrote a giant survey about that, and that's what I do. And it has, here is an answer. The answer is this function, delta should not be in sharp P. And sharp P means it shouldn't count anything that can be tested in polynomial time. So when you count the objects, how do you know if an object is something that you want to count? You look at the object, and you should be able to decide in polynomial time if this is the object that you want to count. Okay, so that's what we do. Now we're into complexity theorem. We're saying that this function is not in sharp P unless something bad happens in computer science. Okay, questions? Go ahead.
So, question about your notion of combinatorial interpretation. Just for example,
I'm not gonna answer that.
That's what
It's not mine, it's computer science. Take it with them.
just your interpretation. Now, do different divisions of equations ever?
Of course.
So now the revolutions are not sharp.
Everything you know, you should read my paper. Sorry, that paper has 2 pages on little Richardson coefficients. Yeah, reading is good. Go read the paper. And the talk is too short for me to give a careful definition of everything. And hopefully by now, people should accept that, yes, notion of Sharpie is the right notion of a combinatorial interpretation. So, I promise I'll answer. I'll be friendly in the future. Any other questions? Go ahead.
Something bad happened in
We're not done yet. You're really jumping ahead. There are 7 levels. 3. And what do you know? We just moved to that level where I'm going to explain what it is. So combinatorial interpretation means the polynomial hierarchy collapses. Again, it will take me a while to explain what's a polynomial hierarchy. Basically, there are problems on the bottom that can be solved in polynomial time, the problems which have 1 quantifier, 2 quantifier, 3 quantifier, all the way, any finite number of quantifiers. The quantifier tend to be alternating. So there this for all, there this for all. And we're saying here that if this function, the difference between the left-hand side and right-hand side of Stanley's inequality has a combinatorial interpretation in formally being in Sharpie, then this whole polynomial hierarchy collapses into a finite.
But it's something very, very good. Everything in polynomial time will be in paradise. It's something really good happening.
Yeah.
That's your
It's another good thing. Oh, hunger is the word. Lots of good things. Not immediate, not very likely in the near future. But could happen.
in what? In the size of the
Yeah, so everything, so n is the size of the poset. Yeah, polynomial in n. And that's so. I'm not defining things carefully, but that's what the input is. You give me the poset and the number h. Any other questions?
Have you put this picture?
Oh, hard. Oh man, just hard. But possible. So this level for prime is basically a level which I'm not going to generalize. I'm just telling you exactly what happened. The polynomial hierarchy is going to collapse on the 2nd level. This is for connoisseurs of complexity theory. Okay, so don't expect this to happen. It's a major collapse of the hierarchy. Roughly speaking, this is saying that if you can solve problems with 2 quantifiers, you can solve problem with any number of quantifiers. Extremely unlikely. That is the point of the result. But we're not done. So there's more. Turns out that, so notice that I never mentioned what is k to k greater or equal to 2. K here is the number of elements that we fix in the poset. Remember we had z1 up to zk, c1 up to ck. So turns out that it's really important for that to be greater or equal to 2. Then and now I'm saying that the equality condition of Stanley's inequality is not in CoNP unless polynomial pair collapses. Now, what does that mean? Basically, let's put here not equal. Not equal means so then there is a witness to prove that they're not equal. Witnesses, if it has a combinatorial interpretation, that's your witness. If the difference counts the number of some tableaus or the number of certain linear extensions or anything like that, then this would be witness. So having equality means that the opposite problem has a witness. And so we're saying that if equality conditions of this inequality can be understood, so you can decide in polynomial time if for a positive element if you get an equality. If that's an so that's an CoNP. Sorry, I think I'm slightly misphrasing it. That's a polynomial pair collapse. Now that is part of another problem that Richard leaves in his paper. One can ask about the conditions for equality, because conditions for equality of this inequality is very hard, and we're saying no, you cannot answer that question. That question cannot be answered. If you could answer it, then the polynomial hierarchy would collapse. See what I mean? I forgot to say everything we did is in joint work with Wei-Hong Chan, who is my former postdoc and currently professor at Rutgers. Everyone good with this? So now instead we started with nice injection, but then we went to combinatorial interpretation. Now we're into equality conditions.
But this does not imply inequality.
So every next level implies there's no next injection.
So how did you get from greater than or equal, from unequal to greater than equal?
So they're positive numbers. I mean, the inequality is already true. Either it's equal or greater or equal.
Can't you have a sequence that goes from up and down, up and down?
No.
But we all-
I have a picture actually later. That's not how it works.
But the point is, there's a sequence in this, right? It's not just one example.
Correct. So n of a. So we have a poset and we have an element, and then we construct a whole sequence. And the sequence is complicated. So we're asking if the equality condition happens for given poset and given the whole input. I just didn't want to write x and z1 up to zk, c1 up to ck. But that's correct. There's a so this each theorem has a lot of prequel to that. Given blah 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 blah, then the follow deciding whether you have equality here is hard in a certain sense, formal sense.
So you know that it's unimoral or something.
Well, it's slope concave by Stanley's inequality. Stanley inequality says that it's slope concave. That's the whole point.
Yeah, log concave is not negative. It implies in unimodal.
That implies unimodality. And in fact, I do have a picture later, but let me look at the time and also tell you. So this is oh yeah, that's a final level. So the main result is this: the equality conditions. Not only they're not in CoNP, they're not in the whole polynomial hierarchy. If they are in some level, then the polynomial hierarchy collapses to like 2 levels without. Okay? So you should not be able to describe equality conditions in any sense. Is everyone okay with this? So polynomial hierarchy is going to collapse. Okay. Yes. In this case, if Stanley's inequality are in sigma m, then pH is going to collapse to sigma m plus 2. It's going to collapse. Just do a little bit about that. Good question. Anyone else? Go ahead.
Can you set for K 1 or 0?
Excellent question. Yes, you're right on time. So for k equal to 1, Schoenfeld and Van Hendel proved that this inequality is the deciding quality is in P. And with somewhat more work, we proved that for k equal to 1, the deciding quality is in P. So remember, k is the number of fixed elements. What's surprising here is that if you look at the proof goes for all k. It doesn't notice the k. But something happens when you have these extra elements, and they make they make everything completely terrible. Okay, and so here is actually the picture that might help. So the way it works is basically in the beginning you have lots of zeros, then there's G-clock concavity here, and then there's sort of like a plateau over there and going down. So what we're saying is that you cannot decide if there are two elements that are on the top. You cannot have equality. You cannot have equality here. Deciding equality there it can be done in polynomial time. Deciding if it's 3 or more here can be done in polynomial time. Deciding whether there's 1 or 2 cannot be done in polynomial time. It's not in NP. It's not in sigma 2. It's not at all. That is the main theorem. So the point is not only so this is sort of the main lemma. The main lemma is saying that deciding whether the two successive numbers are equal is not in the polynomial hierarchy and that polynomial hierarchy. Okay, so it looks much simpler and much more approachable than standard inequality, but that is the stepping stone that the Combinatorics discovered to prove it. And I have a couple of minutes and just a couple of slides. So one of the key lemmas that we need is a celebrated result by Breitler and Peter Winter, which says that the number of leading extensions is sharply complete, so it describes any problem with a plus sharply. So this is for those who figured to leave the time where that is how people counted. Is the statement clear? And we needed a lemma, a rather pretty result, very recent result by Kravitz and Saar, that if you look at, consider a set of values of all linear extensions of size and with width 2 as then this set of values is actually has an exponential sequence from 1 up to 2 to the n over log n. That's another lemma that we needed, and the proof of that Euler's continuous function, which is not a giant surprise because that's how you can construct process for width 2. And a very final ingredient that we needed, everything else we did by ourselves, is sort of Yao and Knuth's analysis of what they call ancient version of Euclid's algorithm, like Egyptian version, which didn't allow division, which allowed only subtraction. So what is the average cost of that? And that turns out to be also small. So not log n that we use for Euclidean algorithm, but roughly log square n, and we needed that as the ingredients for the proof. And on that note, happy birthday, future.